Ah, there we are. Okay, so we were discussing snakes all over the break, but now we're back to snakes as in integrals, and they're always friendly and nice and not scary. And we want to discuss triple integrals. And what I'm going to do over the next, let's say, 20 or 30 minutes, I'm just going to review the entire theory of triple integrals without proving anything. And what you should feel is that it really is just generalizing everything we already know for double integrals. Okay? So let's first wave our hands a bit. For double integrals, there were two variable functions whose graphs looked like this, living over some domain D, and what we were looking for intuitively was the volume under the graph. So when there are two variables, two snakes, what we get is a three-dimensional result, volume, under the graph of a function over a domain D, intuitively. Do you agree? Now think three snakes. The functions are going to be three variable. It's going to be f of x, y, and z. We can't picture it anymore. For any point x, y, z in 3 space, in R3, there's going to be a value, call it w, in some fourth dimension, and I can't draw it anymore. Do you agree? Okay? And the integral, so the domain in x, y, z is going to be some big potato in 3 space, okay? And we're looking for the 4-dimensional volume under the graph of the function, which is defined on some potato, and the 4-dimensional volume is under the graph, which lives in some fourth dimension that I can't draw or see, and I'm just doing this so you can see how helpless I am. Is that clear? Is the idea clear? Okay, so no hope whatsoever of drawing pictures. Do you agree? Anything we can do now is only going to be restricted to saying stuff about the domain. The domain we can still draw because the domain is 3-dimensional. The domain of f of x, y, z. Okay? F itself lives in some fourth dimension, which we can no longer draw. Okay, maybe some of you feel that you can imagine it. We discussed that previously, but we can't draw it. Is that clear? Okay, so, and once you accept that, everything really goes along the line of double integrals. Okay, so V is now a domain in R3. Okay, so V is some big potato. And f of x, y, z, a 3-variable function, is defined on V. I'm calling it V rather than D to indicate its volumishness. Voluminous-ish, I don't know. To indicate that it's 3-dimensional. Okay? So this is V and f is defined on it. And let's draw a little picture here. So now we're looking at 3-dimensional space. V is some form of potato. And to indicate that this is a potato rather than a flat surface, I'm going to add some perspective here. Okay, so can you imagine now a 3-dimensional object? This is the domain of the function. Okay, the function itself, on every point x, y, z, the function has a value. And again, I'm doing this not because it's up there, because it's in some fourth dimension, on some fourth axis. Okay? How am I going to calculate the integral? How am I going to calculate I'm not looking for the volume of this thing. I'm looking for the 4-dimensional volume under the graph over this thing. Clear? Everybody with me? Facing the challenge of 4 dimensions. Okay? So how am I going to calculate it? So I'm going to do exactly what I did in 2 dimensions. I'm going to divide this domain into what? What's the partition going to be into? In single variable, it was into little subintervals. In 2 dimensions, it was into little rectangles. What's it going to be into now? Cubes. Little cubes. Okay? So you should think of taking this domain, going to the supermarket, and then you have that machine that slices bread. Okay? So you have to put it into the machine, and then it makes it into slices like this. Then you have to take it, rotate it, and put it again into the machine. Then you have slices like this. And finally take it again, rotate it like this, and put it again. Okay? 3 times, you're going to get, in all 3 directions, you're going to get little cubes. Can you picture that? Can you imagine that? Everybody? Okay? Now, drawing this gets very messy. Okay? So I don't want to draw lots of lines like this, and like that. But what you should imagine is that we partition V into little, friendly, cute cubes. Okay? So each cube is going to be, when we chop it up like this, and then we chop it up like this, but then we also chop it up like this. So this is, you should somehow picture these little cubes forming up when you chop it up in all 3 directions. Can you see a cube there? Okay? Yes? No. We usually our partition is parallel to the axes. Okay? So it's going to be little cubes. And again, we're not looking for the volumes of these little cubes. These are just the base on which we have to multiply by the value of f. Okay? So Riemann sums, Riemann is, I always forget this. It's either double M or double N or double both. I think it's only double N, but I'm not sure. This is so embarrassing. Can somebody check? 2 M's? Is this correct? Okay. So Riemann sums are going to be now, are of the form sum over I, sum over j, sum over k, f of evaluated sum points ci, dj, ek, times delta xi, delta yj, delta zk. Okay, so this is summing up the 4-dimensional volumes, 1 dimension, 2 dimension, 3 dimension, 4 dimension, 4-dimensional volumes under the graph of f. Okay, and as we refine the partition, and as we refine the partition, in the limit, we get the triple snakes. Triple integral over v f of xyz dx dy dz. Okay, clear? Now you shouldn't be too concerned about these triple summations because we hardly ever use them. We hardly ever use them in Calc 1. Okay, these are just the theoretic foundations for this, but then we have better ways of dealing with these things. And the better ways are going to be to write it as iterated integrals. So let's do that. Calculating things like this is possible when V is simple. So what's a simple domain in 3 dimensions? Remember that in 2 dimensions, we said that a domain which we call D is simple if the x's are between fixed a and b, and then for every x, bless you, the y's are between 2 functions, y1 of x and y2 of x. So what's going to be a simple domain now? So here's an attempt to draw it. And again, there are going to be various versions of it depending on which variables we fix between constants and which variables between functions. But one example of a simple domain, so this is x, this is y, and this is z. So a simple domain would be, for example, the x's are going to live between two constants, a and b. So the x's are between two constants. For every x, the y's are going to be between two functions of x. So we're going to have, let's say, y1 of x and y2 of x. So what you should see so far is a simple domain in the xy plane lying here on the floor. Do you see that? Okay, so you should look at this like this, turn your head like this, and in fact look down on the floor, but this is just in perspective. You should see a simple domain. Let's use some colors. You should see a simple domain just in the xy plane, like this. Do you see that? Okay, but this is not v yet. This is just the projection on of v on the xy plane. Now, for every xy, remember, x is between a and b, x is between a and b. For every xy is between y1 of x and y2 of x. And for every x and y, z is going to be between two functions of x and y. So there's going to be some, now let's use the colors. There's going to be some function above this domain, some function over here maybe. This is going to be z1 of x and y, where this is tricky to draw. You're going to have to use your imagination. So this is the graph of z1, which lives above this domain here. This is the domain. And then there's the graph of another function up here. This is z2 of xy. Okay? And the domain v is this thing. V is this thing. So this is V. Okay, this is dotted. This is in the back. No, this is in the front. Sorry, this one's in the back. Clear? Can you kind of imagine it? Okay, so z is between z2 of xy and z1 of xy. So this is a simple domain. Is of the form okay, and of course the order of the variables can differ, because you can have y between two fixed constants, and then the z's between z1 of y and z2 of y, and then the x's between x1 of y and z and x2 of y and z. Okay, is it clear? Is the idea clear? Okay. Now, when the domain is simple, by the way, let me add one more notation here. If this is V, we will denote, and this is useful, we will denote its projection, the shadow it makes on the xy plane. We're going to call it d sub xy. Okay, so dxy is a simple domain in the xy plane, in the sense of simple domains in two variables. Okay, so once you have a picture like this, the triple integral over v, when v is simple, of f of xyz dx, dy, dz equals the integral from a to b dx of the integral, let's add the names of the variables. X goes from a to b, of the integral y goes from y1 of x to y equals y2 of x, dy of the integral from z equals z1 of xy to z equals z2 of xy, dz of f of xyz. And this is the iterated integral form. And if you look at the inner one, x and y are now constants, are now parameters. We only solve it dz, okay? And then after we solve it, we plug in the z's. Z is going to be gone. They're going to be left only x's and y's. And then you continue to the next integral. After you solve it, they're going to be left only x's. And then you're going to integrate that dx, and you're going to be left with a number. Okay, we'll do examples, of course. Okay, this is just, sometimes it looks scarier in formula form than when we actually solve a concrete example. Okay? Is it clear? Is it clear what happened here in principle? Okay? Okay? One remark, sometimes you're going to see it written, sometimes we're going to write it. So another way of writing it is as a double integral over the domain dxy, dx, dy of, and then there's going to be a single integral where z goes from z1 of xy to z goes to z2 of xy, dz, and then you have f of xyz. This is writing the exact same thing, but instead of breaking it right away into the three iterated integrals, breaking it first into an integral over the domain D of the iterated integral like this. And sometimes in terms of thinking, it helps to do it in steps, to write this first. Okay? So here D, so here V is simple in R3, and here D is the projection of V onto the xy plane. Clear? Okay. Now what we need is how do we change variables in triple integrals? Oh boy, this is going to be scary. So this is like the longest formula I'm probably ever going to write in this course. But again, when you do concrete stuff, the things get simpler much faster. So change of variables So we're going to have this Jacobian. J is going to be, let's call the variables u, v, and w. So it's going to be dxyz to du, v, w. These are the new variables. And by definition, it's a determinant, a 3x3 determinant this time, where what you have is the partial derivative. So you have xu, xv, xw, yu, yv, yw, zu, zv, zw. So this is the Jacobian. And now I'm going to change font to David 6. I don't know. I have to use smaller font because it's going to be very long. So the integral over v of f of x, y, z, dx, dy, dz equals the triple integral over a new domain, which let's call it big W. So these are D and E in double integrals. Now we're calling them V and W. And now this is going to be du, dv, dw. These are the new variables. Here we're going to have this Jacobian in absolute value. And this is already shorthand because it's this big thing, right? And then here we're going to have the function f evaluated at not x, y, z, but rather x of UVW, y of UVW, z of UVW. And I was just too generous. Clear? Again, we'll do examples and you'll see that in practice, the examples are not, they're more complicated in the sense that there's more variables. Okay? But other than that, the ideas are precisely the same as in double integrals. It's not a new theory. Okay? Okay? And of course, this is just the formula, the more precise theorem, which I'm not going to write, assumes that the Jacobian is non-zero on the domain, or at least except maybe points or lines or two-dimensional regions. That's okay. It can now be zero on an entire plane. When you're doing a triple integral, it doesn't see a two-dimensional surface. And that the map defined by x, y, and z has to be invertible, and so on and so forth. Okay, so the final thing I want to say about triple integrals before we dive into examples is a bit about their applications and what we're going to use them for. So, first of all, there's no reason whatsoever to think that double integrals is the end of the road, because if there are functions of more variables, then there should be integrals of more variables and derivatives of more variables, and there are. And in applications, in real life, there are functions of many, many, many variables. Okay, you want to think of anything you can think of in economics or in, I don't know, in engineering, whatever. Once you have more variables to the experiment you're doing or to the theory you're building, you're going to have 5 variables, right? Temperature, the 3 coordinates of space, and the time. There you go, you have 5 variables. Okay, and a function can depend, something can depend on all of those 5, right? So, useful in models, in mathematical models with greater than 2 variables. And I just wrote everything for integrals with 3 snakes, but I'm not even going to write, because it's exactly the same, to do integrals with 4 snakes or 5 snakes or 6 snakes or 17 snakes. Okay? Now you can ask, are we going to get on our exam to calculate an integral with 17 snakes? The answer is no. Yes. Well, you're going to get one, but just for you. Okay? No, the answer is obviously not, and because it just takes a while. Okay? But in principle, theoretically, there's no difference whatsoever. If your domain is simple, 17-dimensional simple, then you can write the 17-snake integral as an iterated 17 snakes, and from there on it's Calc 1, right? Okay, nasty Calc 1, but Calc 1. Okay. One remark maybe is that the volume of a 3-dimensional domain V equals, tell me if you agree, the triple integral over the function 1 evaluated on v dx, dy, dz. And this is on its three-dimensional volume. Do you agree? It generalizes the fact that if you take the double integral of 1 dx dy, you get the volume of, you get the area of the domain, right? Does everybody understand why this is true? If you understand this, you got the four-dimensional intuition. You understand the four-dimensional intuition. Good? Everybody? Don't be shy. Okay. I never know when you're just embarrassed to ask, and if you are, you can ask me later. That's fine too. But if you don't understand, you can be 100% sure, that's a theorem by Weierstrass, that there are other people sitting here that don't understand either. Okay, so don't be afraid to ask. But if I'm just being redundant and everybody understands, then let's move on. For example, a specific form of questions that appear often, and it's just to scare you. It's nothing beyond the math. So if you have, well, maybe I don't want to. Okay, so when we discuss mass, for example, and when we discuss the center of gravity, it's called, or center of mass. We're going to see. We'll do examples of all kinds of physically oriented applications of these things. And these are just a few words that you have to kind of write the corresponding integrals and understand the very basic physics behind it. And then it boils down within one sentence to calculating something like this, or with an actual f here. Okay? Okay. Good. So this was just an introduction. The entire theory for three variable integrals, triple integrals. And what I want to do in the next following clips is start calculating. Okay? So we're going to do, first of all, a couple of examples where we just have a simple domain and we want to write the integral as an iterated integral and calculate it. And then we're going to see some domains where we first start going to do some change of variables. And there are going to be some changes of variables which are very ad hoc-ish. So they're just for a specifically prescribed example. And others are general, like changing variables to what are called spherical coordinates, or changing variables to what are called cylindrical coordinates. And we'll do those. We'll calculate the Jacobian, and we'll do examples. They're a bit more intriguing because it requires three-dimensional perspective. Okay, so the domains are now in three space. Okay, but that's all there is to it. So examples coming up next.